There are two main ways that we can talk about geologic time. The first is through relative age dating, so in what order events occur. But we can also talk about absolute age dating, where we look at the rocks and try to understand exactly how many millions of years have passed since that rock was formed. We call that absolute age dating. And one of the main techniques that scientists use to understand this is called radiometric age dating. It's based on the radioactive decay of certain elements. In order to demonstrate that, I've gathered some things here in the kitchen. We've got several colors worth of grapes here and some cranberries. I have built an atom. Okay, so this is the nucleus of an atom minus the electrons. We have 19 protons and we have 20 neutrons in red. And those represent a potassium-40 isotope. Potassium-40 is slightly radioactive, but radioactive very slowly over a long period of time. What that means is that over time, my nucleus is slightly unstable and it wants to, over time, lose one of these protons, which means it's no longer potassium. It actually becomes an argon nucleus, a different element. This occurs over a very slow period of time. It actually takes about 1.25 billion years for half of the potassium-40 nucleuses to lose their proton or degenerate through radiation. We can demonstrate how we use that to date rocks by these cranberries. Because we know the rate at which the potassium-40 breaks down, we can then apply it to the amount of potassium versus argon in a given rock. Assuming that when the rock first cooled from molten magma, it was just pure potassium, which is typically the case. So we can measure the amount of argon to kind of understand how long it's been hanging around. So I've got cranberries here, and if the half-life of a specific isotope like potassium-40 is 1.25 billion years, then I would expect that after 1.25 billion years, half of it would go away. And so half of my cranberries would go away and be replaced by an equal amount of, in this case, these dried cranberries are my argon. And I can measure the amount of argon versus the amount of potassium. And it tells me how much of that half-life has passed. Now, if I wait another half-life, which is another 1.25 billion years, for a total of 2.5 billion years, I can take away half of the remaining potassium, and I can replace that with argon. And so now I only have about 25% of the original potassium that was formed. I can measure this and try and understand how much time has passed based on the relative amounts of those daughter elements to those original parent elements like potassium. So scientists use these radioactive methods, and that's how we get numbers like this igneous rock was formed 450 million years ago. It's because we've measured that, and based on its half-life, that's approximately what the age calculates to. Now, if there were other elements and other argon in the rock at the time it formed, it could mess with those calculations. So we generally offer a range of dates, rather than a specific one, because of the error involved in the calculation. That is radiometric age dating.